All right, guys, Dr. Colbreth here with a quantitative example of 2D interference. So here we have a setup with two speakers and three guys, Curly, Larry, and Mo. And part A of the question says, if Larry hears a maximum intensity, what does that tell us about the sound produced by the speakers? So Larry is right here, and the key insight here is that Larry is equal distance from both the top speaker and the bottom speaker. So the sound waves travel the same path length to reach Larry. So the fact that Larry hears a maximum intensity tells us that the initial phase of the speakers must be zero, that the speakers are producing sound waves that are in phase. So for part A, we can say that the difference in the initial phase is equal to zero because Larry hears this maximum intensity. Now part B says find the lowest two frequencies that produce a maximum sound intensity at the positions of Mo and Curly. Now Mo and Curly are both 1 meter above the center line here that Larry is on, and so it's an identical situation. Curly is closer to the top speaker than he is to the bottom speaker, and Mo is exactly that same distance closer to the bottom speaker than he is to the top speaker. So let's just consider Curly's position here and go ahead and do this calculation. So in order to calculate whether we're going to have a maximum sound intensity, we're going to have a maximum sound intensity when the total phase difference between the waves is equal to some multiple of 2 pi. And the total phase difference, the expression for the total phase difference, is 2 pi over lambda times the distance in the path traveled plus the distance in the initial phase. Now, we've already determined from part A, the fact given about Larry hearing a maximum, that the initial phase of the speakers must be equal to 0. In other words, the two speakers produce sound waves that are in phase. And so our phase difference between the two waves is only going to depend on the path length difference, delta r. So that's what we're going to need to calculate next. So I'm going to go ahead and draw a line from the speaker to Curly, and draw a line from the bottom speaker up here to Curly. I'm going to call this guy R1 and this one down here R2. And let's go ahead and give this 1 meter a name so we can work symbolically. I'm going to call it D. So first let's write down the expression for R1, and we just have to do a little Pythagorean theorem here. If I draw a line straight out from the top speaker, okay, that's going to be the base of this triangle, which is our length D1, which is given to be 3 meters. And then we need to go up a distance to Curly. And this distance right here from the line that goes straight out from the speaker up to this position, the position of Curly, is given by this 1 meter minus the half the distance that separates the two speakers. 1 meter goes all the way from the center point between the speakers up to our point of interest here. And so we have half this distance, D2, and so we're going to have 1 meter minus half that distance, D2, is going to give us the height of this triangle right here, this length right here. So writing that down, we're going to have the square root of D1 squared plus D minus D2 divided by 2 all squared. And R2 has the same base, D1, okay? But in this case, we have that the height is D plus half the distance, D2 here. So this is D1 squared plus D, which is our 1 meter, plus half the distance that separates the speakers, which is D2 over 2 squared. So now what remains is just get some values for these expressions. We're going to get R1 is equal to the square root of 3 meters squared plus 1 meter minus D2 is 0.75, so 0.75 divided by 2 is 0.375 meters all squared. And plugging that into your calculator, you get a value for R1, which is 3.064 meters. Okay, now we just need to repeat that process for R2, plugging in some values. We're going to get the square root of 3 meters squared plus 1 meter plus, in this case, 0.375 meters, all squared. Plugging that into our calculator, we get a value for R2, which is equal to 3.300 meters. So in order to calculate the phase difference, we need the difference between these two paths. So we're going to get to the path length difference, delta r, is equal to r2 minus r1, which is equal to 0.236 meters. All right, so part B asks for the lowest two frequencies that produce the maximum sound intensity. Okay, the lowest frequencies correspond to the longest wavelengths. So in other words, we want the biggest wave length that's going to fit in here that's going to give us R2, which is longer than R1. And so the biggest wavelength is going to correspond to the lowest two frequencies. And so let's go ahead and return to this expression here for the total phase difference between the waves. We get the total phase difference must be a multiple of 2 pi, and that's going to be equal to 2 pi over lambda times our path length difference, delta r. So the 2 pi's are going to cancel. So we get that m times lambda is equal to delta r. So the longest wavelength is going to be the fewest number. We want the fewest number of wavelengths to get delta r. That's going to maximize lambda in this case. So we want m equal to 1 and m equal to 2. That's going to give us the two wavelengths that we're interested in. And so let's go ahead and solve this for lambda. We get that lambda is equal to delta r divided by m. And the problem asks for the frequency, so we do need to apply the velocity relationship. The velocity is equal to lambda times the frequency, or lambda is equal to the velocity divided by the frequency. Go ahead and plug that in up here. We're going to get the velocity divided by the frequency is equal to delta r divided by m, or the frequency is equal to m times v divided by delta r. Okay, so the first frequency is going to be equal to 1 times the speed of sound, which is 343 meters per second, divided by delta r, which is 0.236 meters. This gives us the lowest possible frequency to produce constructive interference. And plugging this into your calculator, you get a value of 1,450 hertz. What's left is just to repeat this process for the second frequency, which is going to be 2 times 343 meters per second, divided by 0.236 meters. And this gives us a second frequency, which will produce a maximum at that point of 2,900 hertz. And as expected, the second frequency is just twice the value of the first frequency because we get 2 wavelengths in instead of just 1, which means that the frequency needs to be twice as high. All right, guys, I hope that helps out with 2D interference problems, and that is all.